Good morning, everyone. Somewhat embarrassingly, I left my name tag in my room this morning, but I think I know most of you all. I'm, as Matt said, Ben Hills. I'm a graduate student at University of Washington, working with Knut Christensen. I'm excited for the session this morning. I don't know much about all these service processes and everything that folks are going to be talking about, but I'm very eager to learn. So I'll just turn it over to Jonathan Wille, who's going to talk about atmospheric river climatology and impacts in Antarctica.
Okay. Good. You guys can hear me. All right. Thank you, Ben, for the introduction. So yes, my name is Jonathan Wille. I'm a postdoc at the Institut de Géosciences et de l'Environnement at the Université Grenoble in France. And today I'm going to be talking to you about atmospheric rivers in Antarctica and all their glory. So first, I want to thank my various co-authors who have helped me with the research over these years, and also thank the organizing committee here for having me speak and meet all these really nice glaciologists and can teach me a few things about glaciers. So let's get into this. So my interest in studying atmospheric rivers started back in early January of 2016 when I was a weather observer in WAIS Divide, Antarctica. And one day, well, this week, we had a very unusual weather. It became incredibly warm, temperatures around the freezing point, and we had these very dark clouds full of liquid water, as you can see in the image there. And throughout the rest of West Antarctica, temperatures went above freezing, and they had a very extensive melt throughout most of the West Antarctic ice sheet, which was very crazy. So after that event, some years later, I wanted to go back and revisit it and see what was happening meteorologically speaking. And when I looked at the satellite imagery, you see like this very stream of clouds coming from the lower latitudes right onto the West Antarctic ice sheet. And it looked very familiar, like this phenomenon that we often talk about in the mid-latitudes, which we call an atmospheric river. They're famous because they cause a lot of rain, a lot of snowfall, and they can make it quite warm. But not much research has been done before about their impacts in the polar climates. To go over more about like what an atmospheric river is, to go over some basic meteorology. So when we talk about atmospheric rivers, we look at images like this, where we're looking at the microwave imagery, which is measuring the water vapor content of the atmosphere. So tropics very moist, poles drier. And you see all the moistures in the tropics, but you see these little fingers extending out to the polar regions. And in our field, we try to develop algorithms to detect these little guys and call them atmospheric rivers. And they are, even though they cover about 10% of the Earth's surface, they are responsible for about 90% of the total polar moisture transport. And a bit more in the meteorology. So basically, they're associated with the structure of an extratropical cyclone. They ride along the frontal boundary ahead of the cold front. And you see, like in the red there, that's the region of the highest integrated vapor transport. But if you want to talk more meteorology with me later, I can get into more details. So let's see, how do I make this guy go forward? Perfect. So in this image here, I've mapped out integrated water vapor over Antarctica, and these little red squares are regions where the water vapor is above this extreme percentile, 98th percentile. And normally it's quite disorganized, but like towards the end of that slide, which I couldn't pause, they sometimes form like very coherent structures. So I tried developing an algorithm to try capturing those shapes. There it goes. And that was from the early January event that caused the melting in West Antarctica in 2016. So the algorithm I developed, basically, it looks for the 98th percentile of all monthly VIVT, which is the V component of the integrated vapor transport, so basically looking at moisture going due southward, or due poleward, I should say, or integrated water vapor over the reanalysis period. And if the thing extends at least 20 degrees in a meridional direction, the algorithm will call it an atmospheric river. And I'll put something like in this image here, where you have two rivers, apparently one by Alaska and one heading towards the Antarctic coastline. Now, right away with that detection algorithm, we can then create a climatology of the atmospheric rivers around Antarctica. In this image here, we're looking at the annual frequency of atmospheric rivers, and they have this nice zonal symmetry about them. And the first takeaway is that they're very rare, actually. Along the coastline of Antarctica, given point, you may have 2 or 3 days of atmospheric river conditions per year. So they're according to the algorithm that I made, they're quite rare. So to get into some impacts now, first I want to talk about their impacts on surface melt in West Antarctica. So in this image here, we looked at all the atmospheric rivers that made landfall around this part of Antarctica, coastline here, and we compiled all the melting that occurred during these landfall times. And the melt is according to a regional climate model known as the MAR. And what we see is that a majority of melt in the higher elevations can be attributed to the atmospheric rivers during the summer and around the West Antarctic ice sheet. And in the winter, majority of the winter melt can also be attributed to the atmospheric rivers in some of the higher elevations. And this is happening basically here, we're looking at, it's quite hard to see, but basically what happens along the Antarctic coastline is when you have an atmospheric river landfall, you have a very high moisture content that brings along, let's say you have clouds full of liquid water, that causes very high downward long wave radiation, and that brings on the melt. But it's kind of hard to see, so I'll move forward here. And the main takeaway from this study was that, there was about 5 melt events in West Antarctica that were very major during the study period. And so in the left plot, I've taken the composite 2-meter temperature anomalies for those events. And then in the middle one, I took the temperature anomalies for every atmospheric river that made landfall. So we're talking 2, 3 per summer, so more frequent. But when I took the difference of those two, we found that basically if you increase the temperature by 1 or 2 degrees, then the average atmospheric river could cause melt. So now we shift our interest to the Antarctic Peninsula, where the rivers are having a more significant impact. And again, here we use our regional climate model to analyze their impacts. And what we found is when we looked at extremes in the atmosphere, so like for instance, temperature extreme of temperatures that are in the 99.9th percentile, so the hottest of the temperatures, a majority of these temperatures were co-occurring with atmospheric river landfalls. And again, with rainfall, about 40 to 60% of all rainfall was co-occurring with atmospheric rivers. And then with melt, about 40 to 60% of melt on the ice shelves and more in the higher elevations of this extreme melt rates, I should say. And the same can be said for runoff, but more constrained to the ice shelf areas. And we also found that on average, when you had an atmospheric river landfall, you had an average decline in sea ice. So what we're seeing in the bottom plot there is that you sometimes have a 10% reduction in sea ice over 2 days after an atmospheric river landfall. When you don't have sea ice, you have the open ocean can now affect the ice shelf, and we found that a lot of the extreme swells were also occurring with the atmospheric rivers. And this schematic sums it up quite nicely. What we see is when you have an idealized river, you have the moisture transport, it gets orographically lifted over the mountains, and then it has this downsloping firn wind. It's sort of a supercharged firn wind that causes very extensive melt ponding and hydrofracturing on the ice shelf. The kind of hydrofracturing that was described in the Roble and Banwell paper that can trigger ice shelf collapse, and that combined with basal melting from beneath could act as a trigger. And also is disintegrating sea ice, allowing the open ocean to apply strain on the ice shelf front, which is also a trigger for ice shelf stress. And what we found is that the collapses of Larsen A, Larsen B ice shelf, and also 60% of all ice shelf, calving events were associated with the river landfalls. So I'm going to move ahead to some results in the snow briefly, because Michelle Maclennan will talk after this more about her results on Thwaites Glacier. But when we can look at the snowfall that occurs within the shape of the atmospheric river, we can compile that snowfall and call it like the AR-related snowfall. And then, so we look at the trends in AR activity during our study period. So you have like increasing ARs in parts of East Antarctica, decreasing in Wilkes Land, and decreasing around the Ross Sea. and we look at all the snowfall according to MAR, and those trends. So you have increase in snowfall and decrease in snowfall in many of the same places. So when you compare trends in snowfall from total snowfall and AR-related snowfall, we find the ARs are explaining a majority of that snowfall. And again, we look at the interannual variability of snowfall and rainfall, and we look at the annual frequency of atmospheric rivers and the total snowfall, annual total snowfall. We find the two variables are highly correlated across most of Antarctica. These little black dots showing where that correlation is significant, and it's covering most of the Antarctic ice sheet, in fact, and rainfall mostly on the coastlines. So briefly, the next steps is kind of identifying why the atmospheric rivers are, what controls their behavior, and where their origins come from. And in this paper from Wille, 2021, he looks at the ARs making landfall in West Antarctica. And when he looks at this plot here showing the 500 hectopascal geopotential height, what it shows is that on average you have a blocking high downstream of the AR landfall. And that is what directs the moisture towards the continent. So now we're trying to focus on what's really controlling the blocking high behavior, and also what's causing the initial moisture export from the tropics or subtropics towards the Antarctic continent. So to conclude, yes, atmospheric rivers, they're very rare, but they have a very disproportionate impact on snowfall and surface melt in West Antarctica and throughout, well, most of the Antarctic ice sheet, in fact. For now, they're a net positive for the WAIS surface mass balance. They cause more snowfall than the melting. But in a warming climate, that could shift and it could become a source of instability. So basically, this research, now I'm working on a project called ARCA, the Atmospheric River Climatology in Antarctica. And now we want to study atmospheric rivers in the future, in the past, ice cores, climate modeling. So I'm always open to suggestions about how we could do this. And so am I work excited? And that will be the end of my presentation. Thank you.
Awesome. Thank you, Jonathan. So unfortunately, we're kind of doing a fast turnover, so no time for questions, but the next speaker is Michelle Maclennan, and we're going to have a nice follow-up to Jonathan's talk. She's going to present on, again, West Antarctic atmospheric rivers, impacts on Thwaites Glacier specifically, and surface mass balance there. Take it away.
Alrighty. Hi everyone, my name is Michelle Maclennan. I use she, her pronouns, and I am a PhD student at the University of Colorado Boulder working with Jan Leonards. And today, like was already said, to follow up Jonathan's presentation on Antarctic atmospheric rivers, I am going to be talking more specifically about the atmospheric rivers that are making landfall over Thwaites Glacier and their impacts on the surface mass balance there. So while atmospheric river events are brief over Thwaites, there are many atmospheric rivers that are making landfall over this region every single year. So the figure on the left might look somewhat familiar because Jonathan showed something similar in his slides. And this is a heat map of the temporal frequency of atmospheric rivers that are making landfall over the West Antarctic ice sheet. And what you can see is that there's a hot spot in atmospheric river activity over the Antarctic Peninsula, which you might expect. And then there's also another hot spot over West Antarctica. But if you look at the Thwaites region and the Amundsen Sea embayment, you can see that there is not necessarily a hot spot in atmospheric river activity there. However, that doesn't mean that atmospheric rivers aren't making landfall over this region. And in fact, we have an average of about 9 plus or minus 4 atmospheric river events occurring there every single year. And that's what this figure on the right is showing. This is a time series of the number of atmospheric river events that are making landfall over Thwaites each year. So you can see we have quite a few events, and there's also quite a bit of interannual variability in the number of atmospheric river events. So some years we only have 1 or 2 atmospheric rivers, and then other years we have up to 15. However, what this shows is that while atmospheric rivers are temporally infrequent over Thwaites Glacier, there are still many events occurring every year. So to think about how atmospheric rivers are relating to the surface mass balance of Thwaites Glacier, we can think about this in terms of extreme snowfall events on Thwaites. So it snows a lot on Thwaites. There's about 125 gigatons of snowfall every single year. And extreme snowfall events play an important role in contributing to the surface mass balance. If you take just the top 10% of snowfall days from 1980 to 2015, these contribute more than 50% of the total surface mass balance on Thwaites during that time. And that's what this figure on the right is showing. It's showing the percent contribution to the total snowfall of just these high snowfall events. And so you can see that in the lower elevations of Thwaites, extreme snowfall events play a more significant role, but even in the higher elevations, these high snowfall events contribute between 30 and 50% of the total snowfall. Now, atmospheric rivers only contribute about 12 gigatons of snowfall to the Thwaites region each year, which is about 9% of the total snowfall. But if we look at these extreme snowfall events, just the top 10%, atmospheric rivers explain up to 40% of these. So atmospheric rivers are closely linked to extreme snowfall events on Thwaites. We can also think about how atmospheric rivers relate to snowfall and extreme events on Thwaites by looking at the seasonal climatology of these events. So the figure on the right is showing a seasonal breakdown of atmospheric river events in red, high snowfall events in purple, and the total snowfall on Thwaites in blue. So we have seasons on the x-axis, starting with DJF and austral summer, and on the y-axis, we're showing the fraction of events that are occurring in each season. So what you might see right away from the high snowfall, which is in purple, and all snowfall in blue, is that there's quite a bit of seasonality to the snowfall on Thwaites. There's much less snowfall occurring in the summer months than there is in the fall, winter, and spring. And this is largely driven by the Amundsen Sea Low, which is a climatological low-pressure system that migrates zonally along the WAIS coastline throughout the year. And this pressure system helps to circulate warm and moist ocean air masses onto Thwaites, which leads to this seasonal snowfall. But then if you look at the seasonal breakdown of atmospheric river events, you can see it looks a little bit different from the snowfall, in that there are relatively more atmospheric rivers occurring in the summer season when compared to high snowfall and the total snowfall on Thwaites. Now, this is important because summer surface temperatures on Thwaites are the highest out of the year. And when atmospheric river events make landfall over Antarctica, they further raise surface temperatures. So when we have relatively more atmospheric rivers making landfall in the summer seasons, we expect that they can raise surface temperatures to the melting point and cause large surface melt events. And in fact, this is something we can see in a case study of a summer atmospheric river that made landfall over Thwaites on February 4th, 2020. This figure is showing a time series of 2-meter temperatures over Thwaites ice shelf, with observations from automatic weather stations in the colored lines and MERA-2 reanalysis in the gray. And what you can see from the figure is that during the time of the atmospheric river landfall, surface temperatures increased dramatically over the ice shelf. They increased so far that they reach the melting point and stay at or near the melting point, or even above it in the case of our observations, for an extended period of time of up to 5 days. And this is the type of summer atmospheric river event that we expect can cause large surface melt to occur over Thwaites Glacier and this region of the West Antarctic ice sheet. And this is what my research group and myself are currently working on and working towards. We're trying to quantify the impact of these summer atmospheric river events, not only on the total surface mass balance of Thwaites, but specifically also on the firn of Thwaites ice shelf. The figure on this slide shows a density profile from a firn core taken on Thwaites ice shelf, with the observations in red. And what you can see is that between 0 and 1 meters of depth, which is on the y-axis, there are a couple of really high-density meltwater layers present in the firn. So the question we're trying to answer in my group is whether these high-density meltwater layers were caused specifically by these summer atmospheric river events. And we're doing so by modeling the firn over Thwaites ice shelf and also looking at the atmospheric patterns and synoptic structures occurring during the time of atmospheric river landfalls. So, to summarize, there are lots of brief atmospheric river events that are occurring on Thwaites every year, and they cause both snowfall and high surface temperatures. Atmospheric rivers explain up to 40% of extreme snowfall events on Thwaites, and summer atmospheric rivers specifically can raise surface temperatures to the melting point for extended periods of time. And this is what we're looking into with our future research. So that concludes my talk. Thank you all so much for listening, and I would be happy to take questions at the end.
Awesome. Thank you, Michelle. So our next speaker is virtual. Might take us a second to switch over. So this is David Schneider giving a talk on Antarctic precipitation circulation relationships in CESM2.
Hello everyone, I'm David Schneider. Thank you for the opportunity to be a part of the 2021 WAIS Workshop. Today I'm going to talk to you about Antarctic precipitation circulation relationships in CESM2. If you don't know, CESM2 is the Community Earth System model. This is the latest version of the model. It's based at NCAR and developed in collaboration with the university community. I am also based at NCAR, and this particular project is in collaboration with the group at the University of Colorado that's led by Jan Lennartz. So if you look at Antarctic snowfall, there's a relatively new data set from Medley and Thomas. This is a reconstruction of the historical snowfall trend based on ice cores collected across the ice sheet. And this reconstruction shows pretty strong offsetting regional signals. So for example, there's a strong positive accumulation trend in the Antarctic Peninsula region and over the Pine Island and Thwaites region. And then on the other side of the WAIS Divide, there's a decrease in snowfall. And there's generally, over most of East Antarctica, there's a snowfall decrease, particularly in drying wildland. And then if we look at what CSM2 shows in its ensemble mean for its historical run, there's about a 10 to 15% increase in the annual snowfall rate from the early 1900s through the 2010s. And the spatial pattern is roughly opposite of what is observed. For example, there's more precipitation in drying wildland and less or even no trend in the peninsula region. So the objective of this work is to figure out to what extent the atmospheric circulation could explain these patterns and could explain the discrepancy between the observed pattern and the modeled pattern. So what we're going to do is adopt some definitions of the southern hemisphere westerly jet strength and jet position. So these definitions come from Thomas Bracegirdle and his work looking at the jet in both CMIP-5 models and in the real world in the reanalysis. And we're going to apply these definitions in the CSM2 pre-industrial control run, and we're going to use the 850 hectopascal zonal winds. So what we're really talking about, this is the wind field. And so the red shading indicates the wind speed. And so we're just looking first at what latitude in the zonal mean is the maximum wind speed. And then at that location, what is the actual wind speed? So the jet position is the latitude and the jet strength is the actual speed. And we're going to regress these indices onto precipitation and onto geopotential height and then quantify what's the precipitation response in terms of gigatons of snow water equivalent for each season, and then use that to look again at the recent past. So jet position is pretty simply when the jet goes poleward, everything kind of contracts towards the ice sheet, and all the storms go in closer to the ice sheet. So you tend to get more precipitation in these coastal regions over most of the continent, except for this kind of Ross Ice Shelf, Western Ross Sea region, where you get less precipitation because of these circulation patterns. And it's pretty similar in every season, except that in the spring and the summer, you have the biggest impact. 6 gigatons in the summer, 14 gigatons in the spring. And then in the middle of the year, the autumn and the winter, there's less of an impact. So if you had a full year go by and the jet is consistently poleward, you'd have about 18 gigaton net increase in precipitation. And that's just 1 year. So that's a pretty small number given the total yearly snowfall. But if the jet position trend was sustained for a number of years, then cumulatively that could add up to a significant amount. Jet strength is a little different. So with jet strength, you get these more wave-like patterns where it's not just zonally symmetric. And so, for example, in the autumn and the winter, so look, I'll kind of trace out JJA, the winds go parallel to these contours. And so you have increased flow onto the peninsula, and then you would have flow from the interior towards the coast, towards Drawney Mudland. And in the winter and the autumn, you can get some really big snowfall anomalies relative to what you get with jet position. So, if a full year went by when the jet was stronger than normal, that would be a net loss of snow, 61 gigatons of snow water equivalent by this estimate. So if we zoom out the picture, so here I'm going to look all the way to the equator. So instead of just regressing these indices on Antarctic precipitation, I'm regressing on precipitation everywhere throughout the southern hemisphere. And we see some significant relationships, both to the tropical Pacific and over Australia and Indonesia. So this is indicative of teleconnections. So there's a wave pattern here that's part of this, and that's part of what's explaining this snowfall pattern on the ice sheet. So here on the left, I'm using the Southern Annual Mode Index, and that relates to variability throughout the whole hemisphere. And then the jet strength indices that I was using are really more proximate to the Antarctic continent. So they're just kind of different ways of explaining the variance. So in a previous paper, we looked at trends in jet strength in the recent past. So it turns out from 1979 through the mid-2010s, there was a significant increase in the wind speed across the Southern Ocean. And here we define jet strength a little differently than the brace girdle indices. We just use the maximum, or we use the average wind speed in this box rather than the maximum wind speed across the hemisphere. But they're pretty similar indices. And through a number of model experiments, we said that this trend in the jet strength was related to this pattern in the tropics, where we have warming SSTs in the Western Pacific and cooling SSTs in the Eastern Pacific. And this is the seasonality of that trend. So this is the trend in that box. And that trend maximizes in the autumn and in the winter. So, and that's pretty important, I think, for the precipitation, because that's when we have the most Antarctic precipitation if you look through the annual cycle. And so if we look compare the observed trends in jet strength to CSM2, there's quite a difference. Whereas the observed trends have an increase in jet strength in every season, the CSM2 does not. So in summary, model and observations agree on a poleward shift in DJF. I didn't show you that, but they do agree on that, and that would contribute to a net increase in precipitation. However, the observations show jet strengthening in all seasons, but the model doesn't. And previous work attributes jet strengthening to tropical teleconnections. So jet strengthening implies a large net decrease in precipitation, and that pattern is a good fit with the spatial pattern in the Medley and Thomas reconstruction. So moving forward, I would like to just quantify these relationships further. So thank you for your attention, and I welcome any questions.
All right, thank you, David. So next, we're going to kind of continue with surface processes. Philipp Arndt is going to talk about observations of widespread through ice shelf drainage of surface meltwater lakes across Antarctica.
Hi, good morning, everyone, especially to the ones on the West Coast who already woke up for this. My name is Philipp Arndt. I'm from the Scripps Polar Center, and how do we get this started? Today I will walk you through a little bit how we've observed a bunch of meltwater lakes on tops of ice shelves drain through the ice shelves across Antarctica and what that might mean for ice shelf stability. So let me take you back to the 1930s and the British Graham Land expedition first. The guy in skis here, Colin Bertram, is exploring George VI ice shelf. He describes it as flat and level, but then it starts to increase at a gentle gradient, and he finds himself on the top looking into a large crater. So he called this an ice caldera, but he didn't know how they form. So now, thanks to science, we have a mechanism that explains this, and we call them ice dolines. So we have a melt lake that sits on top of a floating ice shelf, and then this melt lake drains through a bottom crevasse, a process that we usually call hydrofracture. And now the water on top that was sitting there was really heavy, so the ice shelf responds to the removal of that large load by compensating for the mass loss and kind of like popping back out. So we could call that like hydrostatic rebound. So how do we observe this? We can't predict these events, so we can't go there and just watch, so we need to rely on snapshots before and after surface elevation. Surface elevation is in green here, so if only there was now a satellite that could measure this surface elevation. Well, of course there is. ICESat-2 has been in orbit for more than 3 years. It's been delivering amazing data of surface elevation, and the green lines here is what we would see. So to blow this a little bit out of proportion, this is what ICESat-2 would roughly see when passing over an ice doline before and after formation. And it also explains pretty well what our early colleague, Colin Bertram, observed there. So now what would this look like in the real world over an actual doline? Well, on the left, we see an ice-covered melt lake on the Amory ice shelf with an ICESat-2 ground track over it. And on the right, there's the photon cloud of ICESat that shows latitude versus elevation, and the red line here is the ATL06 land ice elevation product, so surface elevation. Of course, this lake drained, and now on the right here, we see the surface elevation. We basically just see a large crater. So if we plot the before and after together, we actually don't just see this crater, but we also see that uplift that we were thinking about earlier around the edges. Now, if we take the difference of those two, just as you see on the left, that looks a whole lot more like what we had in our thought experiment earlier. So now, how do we find these dolines in ICESat-2? Well, Roland Warner, an ice sheet modeler at the University of Tasmania, was trying to track the bushfires via satellite, but he very quickly got distracted by Antarctica and found this massive hole on the Amory ice shelf. So he messaged Helen and was like, how do I find out more about this? And it was very late on the West Coast, so she just sent him a link to Open Altimetry. That's an interactive visualization tool for ICESat-2 data. And next thing we know, next morning, he had figured out that this thing was a gigantic doline on the Amory. And then about one and a half years later, we published a paper on it. So this is the ice doe line location, and here on the right we see before and after images. The colorful lines are ISAT-2 ground tracks, and just the dimension of this is something like 3 or 4 miles across the basin. So in the ISAT-2 data, we see not only that collapse space information, but also the flexural uplift. To take this a step further, we created digital elevation models from World War III stereo image pairs, and took the difference between the before and after elevation, accounting for ice flow, and the result is this like 2D surface elevation change model. So putting this all together, we estimated that roughly 700 million cubic meters of water drained through the ice shelf in less than 70 hours. And that's about 300,000 Olympic swimming pools, like 2 trillion cans of beer. Nobody can imagine that, so we made a little plot that shows just how much water drained through the ice shelf there. Now, after the paper, I just looked around Antarctica trying to find more ice doe lines, and REMA shows all these craters on different ice shelves. So in George VI, all these are probably drained meltwater lakes, and so are those on the Wilkins. So now I compiled a list of where we actually observed the formation of a doe line by a satellite in different places. And it turns out that we've observed this across many of the ice shelves across the entire continent. And here, yeah, that's just a few more nice examples of those. So now what can we actually do with this doe line formation data? The viscoelastic flexural response to lake drainage has mostly just been modeled so far. But now if we add another even later ISAT-2 track to our earlier example, we can actually take this data and like our observations and compare it to the model. Now here the color schemes are matching, so we can see that qualitatively this roughly lines up. If we were to do this more quantitatively, it would probably help us understand more about the mechanical properties of ice shelves and could help us improve future models, maybe. So another characteristics of ice doe lines is that where they form, the ice must actually be floating, otherwise there will be no hydrostatic rebound. Here, Fricker and others in 2002 used this to argue that this doe line here on the Amory, that portion was floating even though people thought it was grounded earlier. So going back to our example, this is actually the case here too. Our doe line is upstream of multiple estimates of the grounding line, but we see that flexural uplift of the ice, so it must be floating here, so we can use this data to improve our grounding line. Now, the really big question is, how do doe lines affect the stability of an ice shelf? When Larsen B collapsed, there were a lot of melt ponds on top of the ice shelf, and doe line formation had been observed prior to that. So now it's pretty widely believed that melt ponding and hydrofracture ultimately caused the collapse of this ice shelf. And now there's a slide missing. How do I stop this? There we go. All right. There was also a paper, a really nice paper written by Ali Banwell and others in 2013. And now, well, maybe if you just quickly look at me trying to recreate a figure here. So essentially, if this is the ice shelf and there's a melt lake in between my hands, and so now this lake drains and the ice shelf flexes like this, then you get a lot of stress right in the middle here, but also just here where my wrists are, I guess. And what they showed is that these stresses can put rifts into the ice shelf, and those rifts, if there is more melt lakes around where the rift forms, these could drain again and form another doe line, and this whole thing could set off like a chain reaction of events, of doe line formation events that would then like keep putting rifts through the ice shelf further and further and disintegrate the whole thing. So doe lines can be pretty bad for ice shelves. Yeah. So there's two possible mechanisms for how meltwater routing could be affected by a doe line formation, and they have opposing effects on the stability of an ice shelf. So if this collapsed basin captures the meltwater, it can't go anywhere else and do damage on other parts, so that kind of stabilizes the ice shelf. Whereas if the uplift is strong enough to prevent the water from going into the doe line, it will flow further downstream where the ice shelf is more vulnerable to hydrofracture, and it will destabilize it. So here's an example from our Amory doe line paper where the doe line basin actually captured the water. You see that the melt channel flows straight into the doe line. And we were able to map that channel with ICET2 here on the left panel. And on the right panel, in the next melt season, we see that the dole line partially refilled for a bit in the blue line, and then it drained again. So the water was effectively removed from the surface. Now, here's an example from George VI, where the uplift of the dole line around it was strong enough to keep the water from flowing into it. So this uplift region acts kind of as a sill or dam to create a big reservoir-like lake. And in the long term, we often observe that lakes form in a ring around the dole line, roughly where modeling would suggest that there's a slight depression in the ice shelf. And these lakes could become dole lines themselves now, and that's actually precisely what we're observing in this example. There's a dole line to start with in the middle, and then we get more and more dole lines around it. So essentially, the ice shelf is just, there's an array of dole lines created next to each other that can seriously destabilize the ice shelf. So where do we go from there? A good start would be to work on automatically detecting dole line formation events to get more data and actually do all these analyses more rigorously. And yeah, this just sums it up. Essentially, we found that there's, meltwater lakes draining through the ice shelves is a phenomenon that's much more widespread than we've thought, and that surface elevation change data from these events can help us improve our understanding of the mechanical properties of ice shelves for modeling, of the grounding zone location, and finally of the impact that surface meltwater has on the long-term stability of ice shelves. So yeah, thank you.
Awesome, thank you, Philip. So next we have Sarah Neuhaus, and she's going to talk about the mechanism for the subglacial formation of cryogenic brines.
Hi, thank you. Oh, I'm short, I apologize. So yeah, thanks. My name is Sarah Neuhaus, and I'm at UC Santa Cruz, and I'm going to talk to you today about a new mechanism for the subglacial formation of cryogenic brines. And this is work that I did with Slavik Tulicic at UC Santa Cruz. So first of all, what are cryogenic brines? Well, they are highly concentrated salty water that forms from the freezing of seawater, and that is as opposed to the evaporation of seawater. Why do we care about cryogenic brines? Well, they are responsible for a significant flux of nutrients to the ocean. They represent a key microbial environment, and they have the ability to precipitate minerals that record past ice sheet behavior. And then also, we're interested in finding water on other planetary bodies in our solar system, and it's likely that these brines are similar to the liquid water that we might find on other planetary bodies, such as Mars, Europa, or Enceladus. So on Earth, where are cryogenic brines found? Well, in the Northern Hemisphere, they're found in deep boreholes that are drilled into areas that were previously glaciated. So if you look at this figure here, I don't know where my cursor is. The black outline represents the extent of ice at the LGM, and all those little black dots represent areas where we have drilled and found cryogenic brines in the pore spaces. In the Southern Hemisphere, we find them in the subsurface of the McMurdo Dry Valleys and also at Blood Falls. We also have found them in two boreholes that were drilled in the seafloor, two Andrill boreholes that were drilled in the seafloor off of Ross Island. And then we find evidence of past cryogenic brines in the form of mineral precipitates at these two locations. So previous ideas of how cryogenic brines formed required the isolation of seawater in a basin. And so what that looks like is you have an ice sheet that advances, it's heavy, it depresses the lithosphere, and in turn it also pops up the crust that's on the edge of the continent, and that creates a forebulge that grows large enough that it's able to cut off seawater from the rest of the ocean. And so in that trough, that flexural trough, you form a isolated marine basin, which is right next to an ice sheet, so it's cold, sea ice forms. When the sea ice forms, it only takes up the fresh water, so it creates this brine that's really heavy, and it falls down to the bottom of the basin and percolates into the sediments. Now, this idea was formed to try and explain the cryogenic brines that we find in the northern hemisphere. So I wanted to see if I could take this and transplant it to the southern hemisphere to see if this could explain why we find cryogenic brines in those two andril boreholes. So this is a picture, a figure showing the site of the two boreholes. And if you can see, there doesn't appear to be any sort of, sill or moraine or forebulge or anything that, in the raw sea bathymetry that looks like it could have cut those two field sites off from the rest of the ocean. And if you look at the depths that those two were drilled at, this is the water column above the seafloor. At one of the sites, it's about 1 kilometer depth, and the other is about 400 meters. So they're quite deep. There doesn't appear to be any sort of, bathymetric feature that looks like it could cut them off from the ocean. So how do we form that cryogenic brine? We see the cryogenic brine in the pore spaces. Well, there is another way that you can cut off these, you can cut off seawater from the ocean, and that is in the pore spaces. So the red line indicates where the grounding line was located at the LGM, and if we had seawater in the sediment pore spaces, and then we covered that up with an ice sheet, then we can cut off seawater from the ocean. We could potentially form cryogenic brine in the sediment pore spaces as opposed to in a marine basin. So I wanted to test this idea, and I did this by modeling the pore water concentration of chloride and delta O18 in a 2-kilometer sediment column, which is repeatedly either covered by an ice sheet or covered by the ocean. So I ran an advection diffusion model. We have our diffusion portion and our advection portion. So for advection, I used density-driven vertical advection because the cryogenic brines are formed up at the surface, and they're relatively heavy, so they have a tendency to fall down via gravity. And I subjected the surface sediments to 3 different types of boundary conditions. So during the seawater, during the periods of time when the sediments are covered by seawater, the surface pore water is reflective of the concentrations in the ocean. And then when the ice sheet is on top of these sediments, I examined 2 different scenarios. The first is when there's freezing at the base of the ice, and in this scenario, fresh water is being pulled from the pore water, and so the chloride concentration increases, and delta O18 decreases slightly due to preferential freezing of oxygen-16. And then the other scenario I examine is when there's melting occurring at the base of the ice sheet. And in this scenario, fresh water is being added to the pore spaces, so the chloride concentration decreases and oxygen delta O18 decreases significantly. And so what I did was I modeled 100,000-year glacial cycles, and in each of these cycles, I assigned a certain amount of time to seawater periods, certain amount of time to freezing periods and melting periods, and I varied those lengths within each glacial cycle. And I ran multiple 100,000-year glacial cycles to see if I could come up with, if I could reproduce the concentrations that we observed in the andril cores. And sure enough, I was able to do so. You can see that my model results fit okay. This is a fairly simplified model, so these fit well enough to show that it is possible to form cryogenic brines in the sediment pore spaces, which is super handy because in the raw sea, we don't, find any evidence of past isolated marine basins. So in conclusion, it is possible to form cryogenic brines in the sediment pore spaces, which is useful because it doesn't require an isolated marine basin, as I already said. And then cryogenic brines may be more prevalent underneath the Antarctic ice sheet than we currently know, because it's likely that there are brines hidden in the sediments where the Antarctic ice sheet is frozen to the bed. So this is a map showing where there is freezing and melting underneath the ice sheet in Antarctica. The blue indicates freezing and yellow indicates melting. And as you can see, the areas where we either find cryogenic brines or evidence of past cryogenic brines falls into this area where there's freezing at the bed, at the base of the ice. And then if we want to go back to the northern hemisphere, you know, we have found cryogenic brines in areas that are currently land, but we might also find them in areas that are currently under the ocean, but were covered by ice in the recent past. So thank you.
Awesome. Thank you, Sarah. So for the last talk of the session, we have one more on we started with mostly surface processes, and then Sarah and Andrew are taking us into more basal processes. So Andrew Hennig is going to give us an overview of quantifying glacial meltwater inventory in Pine Island Bay from 1994 to 2020 using seawater delta 18O isotopes.
Hi everyone, happy to be here. I'm going to talk to you a little bit about measuring glacial melt using seawater isotopes here. So as we're all aware, West Antarctic ice sheet, we're losing mass. This has been correlated with areas where there are marine grounded glaciers and areas where the deep waters are warmer. The idea being that you have the warm circumpolar deep water being brought up onto the shelf, getting in underneath floating ice shelves, leads to thinning and further retreat. So what I'm going to show you here is I have almost 1,300 Delta 18O samples collected from Pine Island Bay over a 27-year period from 1994 through until 2020, and I'm going to show you how we can use those measurements to directly measure the presence of meltwater. So if we go back to 1985, Stan Jacobs showed that we can look at the evolution of Antarctic water masses as mixtures of circumpolar deep water and different freshwater masses or circumpolar deep water undergoing different freeze-melt processes. So freshwater is all going to decrease the salinity of our circumpolar deep water, but by using oxygen isotopes, we can determine the specific source of the freshwater. For instance, glacial meltwater has a very strong negative delta 18O isotope. And just for clarification here, when we're talking about oxygen isotopes, we're talking about the isotopes of the oxygen in the H2O molecule rather than dissolved oxygen or anything like that. So in the Amundsen Sea, we can use a 3 end-member mixing approach. It uses the modified circumpolar deep water, sea ice melt, and glacial melt. We're going to define our modified circumpolar deep water individually in each year based on observations. This is due to interannual variability because of wind forcing and things like that. We're going to define our sea ice end member based on analyses of previous experiments done by Meredith et al. And we know that glacial ice is going to have a salinity of 0 because it's fresh water. But how do we know its delta 18O value short of getting up underneath these floating ice shelves and knocking off a chunk of ice? Well, if we go ahead and we plot up all my delta 18O data against salinity, and we look at just the subsurface waters here, there's different freshwater sources. You have sea ice melt, precipitation, glacial melt, but our precipitation and sea ice melt are going to be restricted to the upper water column. So any freshwater intrusions we see below the surface mix layer must be glacial. So if we plot up all of our delta 18O data against salinity and then determine the slope, which is essentially the same mixing line that we saw just here, all the way to the 0 salinity intercept, we can see our freshwater end member. And if we jump through our years from 1994 to 2020, we can see that the intercept remains remarkably consistent year to year. Our nearest ice core is the ITAS-02, and it shows values about -34 to -26 per mil. Local precipitation in the area has a value of about -15 per mil, and so this tells us that our freshwater end member in the subsurface here is indeed glacial melt. And for my calculations going forward, I've used -29 as a steady end member for our glacial melt. So if we plug into the system of equations I showed there earlier and calculate my glacial meltwater fractions, we can see that we have a really consistent vertical structure of our glacial melt from year to year. We see our greatest meltwater fractions toward the surface. This makes sense. Fresh water floats. It's less dense than salty water. We also see a sort of pseudo peak around 350, 400 meters, which is coincident with the draft of the Pine Island Glacier, which again suggests that, okay, these are in fact glacial meltwater signals that we're seeing. We see little to no signal of glacial melt below 600 meters here. And now if we look at all of these data year to year and then vertically integrate our average meltwater content, we get something like this. And it looks like our average meltwater inventory in the bay has actually remained remarkably consistent year on year from 94 to 2020. And while that seems a bit funny given the acceleration that we've seen from all of our remote sensing based estimates, and so why might that be? Well, you know, one possibility is that these high basal melt rates date back further than we previously suspected, but there's some kind of lag time between the response of the ice shelf itself. It's also possible that as we've seen the polar westerlies increase in magnitude and shift poleward since the 70s, and this has increased the amount of circumpolar deep water brought up onto the shelf, and therefore increase in our circulation rates, and it's kind of obscuring the signal as these melt-rich waters are also being cycled out as the melt increases. And finally, it's also possible that since most of our mass loss is actually in the form of calving icebergs, that the signal is being exported off-shelf rather than being able to be detected locally, since it's, you know, melting off in the Southern Ocean. However, if we look at our circumpolar deep water itself, we can see that we actually have a strong linear decrease in the delta Tino of our circumpolar deep water, particularly between 2007 and 2020. Now, what's a little bit funny about that is we don't see an associated decrease in salinity. The decrease in delta Tino does suggest that we're seeing an increased presence of glacial melt in our circumpolar deep water, but then why aren't we seeing salinity compensated? Well, our salinity could be compensated because of the increasing sea ice production we've seen. Of course, that's a brine rejection process, and we have these salty brines being rejected, therefore compensating the salinity while still having an overall negative shifting impact on the delta Tino. And recent study by Schubert et al. And also Andy Thompson, who we saw speak yesterday, showed that we're having a glacial melt from the Bellingshausen becoming entrained in the ACC, which of course are source waters for our modified circumpolar deep water. So that would be another point that would suggest that, you know, we are seeing more glacial melt in the CDW. So some key takeaways here, well, is that I hope I've convinced you that seawater oxygen isotope data provides us a way to measure glacial melt in a direct way that's independent from any of the sort of other methods that we might use. Also intriguing that at least the standing meltwater stock in Pine Island Bay has remained kind of remarkably steady between 1994 to 2020. Though that doesn't necessarily mean that that's what the melt rates have been doing. And finally, we've seen the delta Tino of our modified circumpolar water decreasing since 2007, again suggesting that we're having an increased presence of glacial melt in that water source. So kind of in closing, I think that using these kind of independent measurements of glacial melt using oxygen isotopes alongside these other kind of remote sensing measures can be a really great two-pronged approach to better understand melting of the West Antarctic ice sheet, where it's happening, how it's happening. And the incorporation of these kinds of measurements into more advanced kind of high resolution ocean modeling could help us actually get a melt rate out of these sorts of measurements. And using these sorts of ongoing measurements of seawater oxygen isotopes, both on the shelf and also I think in the off-shelf waters of the Antarctic circumpolar current gives us another tool to monitor the kind of fast changes that we're seeing in the Southern Ocean and around the West Antarctic ice sheet. Thank you.
Awesome. Test. Test. All right, great. Thank you so much to all of our speakers. Can we get the in-person folks to come up for a quick discussion round? And Julia Andreasen is here helping me with some of the virtual components. So we're also going to be looking for questions from you all who are tuning in from abroad. So please ask away if you have questions there. And if we missed anything, if questions came up during the talks, please ask them again. I don't want to lose anything that was being asked during the talks themselves. Just as a quick kind of refresher, we had a couple talks in the beginning about surface processes, atmospheric rivers, and then we had the virtual talk about precipitation, circulation, coupling in model, and then Philipp gave us a talk about through ice shelf drainage, so surface processes, and then we switched to some more subglacial processes with Sarah's talk on cryogenic brines and Andrew talking about subglacial meltwater. So I might kick it off with more of a discussion question to the folks talking about surface processes. I generally, I started thinking about Greenland. I've shifted towards Antarctica now, but when I did my master's degree, I was thinking about Greenland a lot, and we think about surface processes more there and how they're kind of progressing. Maybe we have melt processes progressing further inland. As we start to think about that more with Antarctica, as we have maybe melt processes going on, we have warmer climate. What things should we be looking out for, paying attention to, as maybe surface processes could become more influential in the Antarctic continent? So anyone who feels comfortable can comment.
Sure, I'll give it a shot. So your question is more of like how melt processes can migrate from the coastline further into the Antarctic interior?
Sure, yeah.
So I think what really controls that is the sort of amplitude of the polar jet and degree of moisture intrusions from the lower latitudes to the Antarctic ice sheet. And like the research I've done, we've noticed that to have melting in the high altitude, more interior regions, you need a very significant deviation of the polar jet and the form of the atmospheric river to have temperatures go above freezing at these elevations, like what we noticed in January 2016 over the West Antarctic ice sheet. But for now, these events are pretty rare, but that's something I want to pay attention to in the future.
Awesome, thank you.
One thing I would add to Jonathan's response as well is that we can look at some of the past extreme events in atmospheric rivers, like the one he discussed, and some of the others, since they are rare, and look at the effects we see on the surface mass balance by these really extreme events that do penetrate quite far into the Antarctic ice sheet.
Just one thing to add, because I'm mostly looking at surface ponding of meltwater, and on ice shelves we actually usually observe that a lot of the melt ponding starts at the grounding line and then kind of migrates outwards. And by the time Larsen B collapsed, for example, at that point there was just melt ponds all over the place, but in a lot of other places we just see meltwater close to the grounding line right now, at least for meltwater lakes.
Well, there is one question. I'm going to just let you take another question, unless anyone
Sure.
else wants to address this. There's a question pressing question for Philip from virtual. So Peter, I might let you go ahead with your question if you had one.
Yeah, sure. Great talk, Philip. So my question is, I wrote it down, so I'd read it out, right? Have you thought about looking into the evolution of ice shelf lakes and dolines into superglacial rivers? Is there any relationship between a critical water volume and the switch between lakes to rivers, or do you anticipate that is primarily forced by localized ocean-driven melting on the ice base? Looking at Greenland ice shelves and tongues might help with this.
I think I missed a critical part there because something was dropped in the room.
I can read it again.
You made a point about rivers. Can you repeat that, please?
Yeah, so I'll just read the question again. Have you thought about looking into the evolution of ice shelf lakes and dolines into supraglacial rivers? Is there any relationship between a critical water volume and the switch between lakes to rivers, or do you anticipate that is primarily forced by localized ocean-driven melting on the ice base? Looking at Greenland ice shelf and ice tongues might help with this.
Okay, yeah, we've looked into the evolution of the meltwater system a little bit. There's a little bit about it in our paper, and then also Julian Spergel, who was also in our paper, has a really nice paper on the long-term evolution of meltwater lakes on the Amory ice shelf as well. In terms of rivers or meltwater streams, usually, I guess what we observe is that they just deliver the water downstream, and most of the time, at some point on the ice shelf, because it just flattens out, you form meltwater lakes further downstream, and also quite often very close to the grounding line, where the flexure of the ice shelf, due to being not grounded anymore, gives you a little bit of a surface depression. I don't really know how much that answers your question, but
Yeah, I could just ping you offline.
that'd be great. Thank you.
Yeah, I just first want to say thank you so much, everyone who spoke this morning. It was a really great session, so thank you. My question is for Michelle and for Jonathan in regards to atmospheric rivers. Obviously a really exciting topic right now, and I'm curious your opinion in regards to, I kind of have two questions. The first is, so as a net, they provide more snowfall than melt. Are there locations where that doesn't stand? Like, are there locations where you actually get more melt than you get snowfall? And then my follow-on to that is really, I think based off of your maps, if I followed, it looked like the drivers of snowfall near the coast, I'm sorry, let me say this again. Atmospheric rivers were significant contributors to the percentage of snowfall near the coast, more so than inland, but it was vice versa for melt as a percentage. So do you think atmospheric rivers are more of a stabilizer or a destabilizer for ice shelf processes?
Sure, I'll talk the melting stuff and do the precipitation, yeah. So the question is, where might the atmospheric rivers be have more melting than snowfall? So I think in the case for Greenland, the atmospheric rivers have become more of a source of melting, at least in the research I've done, than overall snowfall, but it depends on the season. It's harder to say for Antarctica. I can say like for the Antarctic interior and most of West Antarctica, they're net positive, but for the Antarctic Peninsula, I don't know if they're necessarily like the melt's beating out the precipitation exactly. And you want to take the next part?
Yeah, so in terms of the stabilizing or destabilizing effect of atmospheric rivers. I think for Thwaites and surrounding regions, they contribute much more to snowfall, but it also snows a lot in this region. So atmospheric rivers don't contribute or contribute less than 10% of the total annual snowfall in this region. So I think as of right now, they act more as a stabilizing effect, since the effect on melt is also still minimal in this region.
And I definitely agree, like, as the climate warms up, there'll be an additional source of moisture transport to the continent, and that will sort of, by the Clausius-Clapeyron relationship, we'll have more snowfall on the Antarctic continent, which will counteract some of the sea level rise. The only place where they could be destabilizing at the moment, though, is from what we see on the Antarctic Peninsula, where the snowfall on the ice shelf isn't so significant, but their effect on the Fernwind and the widespread melt pond formation and the stuff with the ocean waves could destabilize like the Larsen Sea ice shelf in the future if the basal melt gets to a certain point.
Awesome, thank you. There's a great conversation happening virtual. Doug McHale has been complimenting some of our speakers. I wonder, Doug, if you wanted to speak out or... Oh, okay. All right. Never mind. You don't need to turn the video on if you would choose not to, but we can also progress forward with an in-person question if that would be preferred. Indrani, would you like to ask a question?
Great talk, everyone. This is Indrani asking a question to Philip. Sorry. So 2 questions. First, when you show the flexure, I wanted to know the time scale that it happens after a melt event has occurred. Secondly, if there is a distribution of those tow lines, how have you seen which sizes or length scales to their progress? Like all of them will not be flexing, I believe. So if you're talking about a collapse, that becomes important. I know this is a work in progress, but I was just curious.
So in terms of length scales, well, for the drainage of the meltwater, at least for our paper, thank you. We constrained everything to something like 70 hours, just using various satellite methods that we can somehow find. There's a few other dough lines that we've observed drain essentially within a day. Like we had daily imagery, and after a day it was there, it was done. And it seems like the ice shelf responds immediately, just elastically flexes up. In terms of how large those are, the Amory dough line that we wrote our paper on was definitely an anomaly. That was a massive one. A lot of the dough lines that we observe are something like maybe 1 kilometer across, sometimes like 500 meters, sometimes even smaller. So that's more usual, I would say, but it kind of depends on the regime on the ice shelf, where they're located, and just how the meltwater gathers in there. And then also on the Amory where we observed this, the ice is really thick, so it makes sense to think that you would need more water to actually make this lake drain all the way through hydrofracture. And then the length scales of the actual flexure of the ice shelf, again, mostly are determined by the ice shelf thickness. So on Amory, where it's thicker, it would be flexing up over a larger area, and on a really thin ice shelf, it would be a smaller area.
Hi, I have a question for Sarah. Really cool talk about the cryogenic brines. And I was curious, when you showed your model results, I couldn't see the numbers, but I was wondering you said that you saw the cryogenic brines in the pore spaces, and I was wondering what the actual signature was that you were identifying, like what was the salinity, were there other indicators? And then I'm curious because I'm wondering whether you considered other possible reasons for changes in the salinity and the delta 18O, like changes in past ocean conditions or possibly geochemical things like methane hydrate precipitation or other processes.
Yeah, so I just looked at chloride and delta O18 because to get rid of the geochemical or geochemistry, because yeah, we know that there's like mirabolite formation, and so I wanted to try and avoid the chemicals that might actually be interacting with this other sediments. And so, yeah, I think it is just ocean signal and, you know, oxygen from the ice. But I just assumed that the ocean properties were the same over the entire, both the ocean and the glacial properties were the same over the entire time frame. So yeah, this was a very sort of simplified model just to see if we could reproduce the profiles that we saw in the Andrel course. Yeah.
Great session, everyone. My question is also for Sarah. I'm really curious about your future steps. So do you think looking at sediment grain size and shape to determine depositional environments surrounding the brines would be helpful? Or is there a way that you could use data to look at brines in those extraterrestrial environments?
Yeah, that's a good question. I did think about grain size for a minute, but I don't have plans to continue. I kind of wanted to look at the northern hemisphere to see if I could, to take this up to the northern hemisphere. Yeah, but that's a really good idea to see if we could try and figure out where we might find brines on other planetary bodies. I don't know enough about that to be able to speak. I know that we're trying to see, there's been arguments about whether or not there's a subglacial lake on Mars. But yeah, I don't know. Yeah, it would be cool to talk.
Yeah, hi. Wonderful session. I have a question for Andrew. That's a very intriguing data set you presented. Really started me thinking, but my question for you is there any data or is there any other information you would need to solve your trends in the oxygen and salinity? What data would you need if there are any?
I guess if we want to trace that back to something about a change in melt rate, like some more kind of advanced isotope-enabled modeling is really, I think, the next step. Again, yeah, so I've got some hypotheses about why the trends seem like a little bit incongruous even with one another. You could see in the 1 year where you do see a kind of a proportionate drop in salinity with the delta 18O is the year 2000. That was a year with kind of anomalously low wind forcing. So I again have hypothesized that, okay, then we're not having water cycled off as quickly, so we're having like greater accumulation there. So it can also go the other way where maybe we have a higher signal, but really to turn it into something more than a snapshot of this is how much meltwater is here at this moment when we're taking our measurements. I think computer modeling and using isotope-enabled ROMs is really the way to go.
Thanks, Ben. So I asked this online, so some people got a little preview of this, but I was thinking about the last two geochemistry talks and then all the atmospheric talks. Do you think we can identify the source of the ARs? Is the source of the ARs different enough from background precipitation that we can actually look at chemical signals and take this back in time in fern cores or ice cores, because then you get some sort of extreme event proxy.
That's actually a very good question. Not a dumb question at all. Actually, it's currently what we're trying to do right now. It's the next step of our research to try to see if we can find a AR signal in our ice cores. And the most logical place would be to look at the delta 018 signature, because they theoretically should have a moisture source region that is of lower latitude than many of the other precipitations around Antarctica. But it's tricky, as we're discovering, because ice cores don't have a really great temporal resolution. You can do maybe a year resolution or even seasonal resolution at best for coastal sites. So for now, we're doing like real-time measurements with sensors along the coastline to see if the AR landfalls match up with spikes in the delta 018. There's also a few other things, like I know I'm working with a group from Hobart, Australia, where we're looking at ice cores from Laudome and Mount Brown South to see if there are other chemical signatures, like volcanic signature perhaps, or other sulfite signatures. I'm not an ice core specialist, but I'm trying to learn about it. But it'd be great, because then it would give us a paleoclimate history of atmospheric rivers if we can actually answer this question. Actually, can I ask Phil a question? So I'm a complete Doline novice, but it was really cool to like see these things actually. Is there like something like special, like is it what atmospheric processes cause them, or is it like the same as like melt pond formation?
Yeah, so it seems like it's the same as melt pond formation. You just gather a lot of melt water somewhere on the ice shelf. And what we've observed is that usually those form over a long time scale. So the big Doline on Amory that we wrote our paper about has been there for the lake that formed it has been there for the entire satellite record. So we couldn't tell how long it's been there, but it had been forming over at least many decades, and then as more and more water accumulated, it just at some point was so much water that the ice broke and it drained. That's our hypothesis, at least.
Hey, thanks, y'all. For our atmospheric river folks, I'd be curious to hear what's your sense of our forecasting abilities, especially for kind of field planning and logistics. It probably sucks to be in the fields during one of these, and what's our ability at this point to say, hey, in 10 days you're about to get slammed or not?
It could be great to be in them if you want to observe them, right?
I think in case it rains and snows and is warm at the same time, it might be slightly uncomfortable.
Yeah, that's a good question. I have a master's student who will try to apply this atmospheric river detection algorithm we've made to a weather forecast model. Let's see if it could actually like give us some advanced warning. Yeah, I've heard in the past there might be some interest in like trying to actually predict these, in regard to like radio sun launches to get more data. But yeah, it would definitely affect your field mission if it happened while you're out there.
Hi, thank you for the talks, everyone. Those were really cool. I actually had a question for Sarah. So I was wondering what other parameters you considered adding to the model, like porosity, oxygen bigacity, like those types of things.
Yeah, so we do consider porosity, and we assume that it's the same all the way through the column, which is probably not correct. I just took numbers from measured cores nearby. But I also consider hydraulic conductivity, and I actually found that hydraulic conductivity had to be quite high, so there's a lot of vertical downward movement to try and explain, to get the signal down. There's sort of a bump further down the core that I was unable to reproduce without significant downward motion, which suggests that there's a lot of fracturing in this area. Yeah, and what else did I consider? Well, we considered density, but that was based off of the density of, the concentration of chloride, basically, was how I assumed density of the pore water. Yeah, I don't know.
I have a question for David. I hope he can chime in. I think if I understood correctly, the CSM2 was able to capture the impact of the jet strength correctly, but that the trends were not correct. And I'm wondering if you know why that is, and then also, is this a problem across multiple models?
Yeah, hello, can you hear me? Yeah, so the reason, what I showed in the trend in CSM2 for jet position and jet strength, the jet position is related to the ozone hole. So that's pretty well modeled, that the response to ozone depletion is a poleward movement of the jet in the austral summer. And so that's considered a forced response. Whereas this variability in jet strength is more related to the tropical teleconnections. So that's internal variability. So you're not going to see that in the ensemble mean of the historical CSM2 runs, because the ensemble mean is the forced response, whereas the tropical variability is internal. So we might see it in, because the ensemble mean doesn't have the sequence of the tropics. So we might see it if we have a large ensemble, which we do now. So we have 100-member large ensemble. So if we get lucky, some of those members might look like what happened in the real world. And then we also have all these pacemaker experiments where we prescribe the tropical SSTs. And so those runs will be ready soon. And so in those pacemaker experiments combine the forced response with the internal tropical variability. So that'll be a really interesting comparison to what I showed today.
Rivers that are making landfall over this region are pretty short-lived. So to see such high-density meltwater layers in a fern core, we'd expect that that might be contributed by a really extreme event, but that doesn't necessarily correlate with the atmospheric rivers we see that have an average duration of like 15 hours or less than a day. So I think there's a possibility that other types of melt events or high surface temperatures could have contributed these layers as well in the fern, but it's possible that they were contributed by atmospheric rivers by an extreme event.
All right, thanks everyone. looks like there has been some interesting conversation continuing virtual, but we don't really have time to go over all of it. I would encourage Philip in particular to follow up with Doug McHale in maybe a setting that he feels more comfortable with. But let's thank all the speakers again, and then maybe grab a round two of coffee.